This is Cisco Training 5. I'm Daryl, and today we're going to build our triangle, we're going to go over static routing, and we're going to talk about Cisco Express Forwarding a little bit. This is the triangle that we're going to build. I have 3 routers. I've called them top, middle, and bottom. That's the same way that they're stacked on my desk so that I don't get them mixed up. I'm going to build a triangle with the serial interfaces. On each of the routers, I took my serial cable, I made the DTE data terminal equipment end and plugged that into the serial 0 interface on one of the routers. And then the DCE data communications equipment I plugged into the serial 1 interface on the other router. That's just so it's easier to remember. You could reverse that if you want and mix them up however you want. Then I've assigned address space for each of my serial interfaces. I've mixed that up a little bit. I have a /30 on this link, a /29 on this link, a /24 on this link. I've also configured loopback interfaces on the and assigned them /32s. Let's go ahead and start our configuration. This is the router at the top. And I did a write erase, so it's asking me if I would like to start the initial configuration dialog. And the answer is no. And I'm trying to type no, and it's sort of hung. And we're back. I had a little problem. I had to kill and restart my Z-term. This is the router on the top. I'm going to go into enable mode, conf t. First thing I'm going to do is configure it with its hostname, top. On my loopback interface, loopback 0, I need to configure it with an IP address 172.16.2.1/32. So int loopback 0, int LO0 for short, IP address 172.16.2.1. /32 is a net mask of 255.255.255.255. Again, that's a special case and I have to no shut. My serial 0 interface is configured with an IP address of 172.16.1.1. This is a /30, so the net mask is 255.255.255.252. No shut. My serial 1 interface, IP address 172.18.1.2. This is a /29, so the net mask is 255.255.255.248. No shut. Now there's something I'm missing. The serial 1 interface is DCE. Let's confirm that. Show controller in serial 1. Show controller serial 1. That's the right command. And I scroll back. And there it is, DCE cable on this side. So conf t int serial 1. I need to configure a clock rate on the DCE side because the DCE side has to provide clock for the line. Clock rate 64,000. Show IP int brief. And there I am. My loopback interface is up. My serial interfaces are down because the other sides are not configured yet. And I will do a write mem. Write mem is where we save the config. That way if we reload the router, it will come back with the same configuration. One of the interesting tricks if you're configuring a router at the remote end of a WAN link is to not write mem. And before you start, you say reload in 10. So now in 10 minutes, this router will reload. If I was configuring it through a WAN link, if I made a mistake and disconnected myself from it, then because I had not done a write mem, when in 10 minutes it'll reload itself and come back with the original config. Once my change is successful, then I do a reload cancel, and a right mem. And there we are. It's building configuration. Takes a while. Okay, so that's it for the top router. Let's go to router middle. Hostname middle. Int serial 1. IP address 172.16.1.2, 255.255, 255.252. No shut. Clock rate 64,000 because this is the DCE side. Int loopback 0. IP address 172.17.2.1. This is a /32, so our net mask is 255.255.255.255. No shut. No shut means no shutdown by default. Cisco router interfaces are shut down. Int serial 0. IP address 172.17.1.1, 255.255.255.0 because this is a /24. No shut. This is the DTE side, so I do not need to configure a clock rate. And show IP int brief. I always do the show IP int brief when I'm done because very often I forget to do a no shut or something like that. So here we can see all the interfaces are no shut. The loopback 0 is up. Serial 0, which is going to the bottom router, which is not configured yet, is down. Serial 1 is going to the top router. It's up. And my IP address is 172.16.1.2. The tops router on that interface is 172.16.1.1. So let's see if I can ping it. Success. The middle router can ping the top router on the directly attached interface. Now let's try to ping the top router's loopback interface. Ping 172.16.2.1. This is failing. And the reason it's failing is because we don't have a route to the top router. Show IP route. This shows the subnets that we know how to get to. We know how to get to 172.17.2.1/32 because that is directly connected. And we know how to get to 172.16.1.0/30 because that's also directly connected on the serial 1 interface. But we don't know how to get to 172.16.2.1. So when we ping 172.16.2.1, the router looks in its route table and looks, how can we get to the 172.16.2.1 net? And it can't. It doesn't know how. So the ping fails. After we configure our IP addressing, we will come back and configure our routing protocol. The other command I want to show you is show CDP neighbor. CDP stands for Cisco Discovery Protocol. And we can see that the device top is out our serial 1 interface. It is a router. It is a 2511. And it sees us at its serial 0 interface. Okay, I'm going to move my console cable to the bottom router now. Hostname bottom. Int serial 0 is IP address 172.18.1.1, 255.255.255.248. That is a /29. No shut. This is DTE, so I don't need a clock rate. Int serial 1. IP address 172.17.1.2, 255.255.255.0. This is the DCE side. Clock rate, I'll go with 64,000. Again, we have a lot of options for the clock rate. If you hit the question mark, clock rate, question mark shows you all the options. 64,000 is reasonably fast, but not too fast. If you went with 2 million and your cable was a little bit weak or, something, you might have some errors or something like that. So I just go in the lab. You don't really need that fast. Clock rate 64,000 is great. No shut. Int loopback 0. IP address 172.18.2.1. This is a /32. No shut. And show IP int brief. And my serial 0 interface is down, down. My other interfaces are up, up. So let's see, on my serial 1 interface, the other end is ping 172.17.1.1, and that is successful. Let's look at my serial 0 interface, show controller int serial 0, try to fix show controller serial 0, I always mess that up. This is supposed to be the DTE side, and it says no cable. That's interesting because I plugged in my cable. So you can see how useful the show controller serial 0 command is. It thinks that there's no cable attached to this, and I believe that there is because I plugged it in. So I'm going to go debug my cable for a little bit. I'll like unplug it and replug it and check the pins. Maybe I bent the pin. And we're back. That was a weird one. I actually managed to plug in the synchronous serial cable upside down. So now, the trick to debugging physical layer problems like that is you want to find a known, you don't know if the problem is the physical interface on the router or if it's the cable. So what you do is you find a cable that you know is good and swap it in there. And you find another router with good synchronous serial interfaces and you use your suspected or unknown synchronous serial cable and plug that into the good synchronous serial interfaces. And that way you can positively, the trick is you want to positively identify whether each component is good or bad by testing it with other known good components. Of course that won't help you if you plug the cable in upside down, but oh well. So here we are, show IP int brief, and we're up, up. So our status is up, so we're up in a physical sense. And our line protocol is up, so we're up in the link layer sense. But we still, if we've typed in the incorrect IP addresses or gotten them wrong, then we will still not be able to ping in our network. So before we bring up routing, we want to make sure that our IP addresses are configured correctly. So on the bottom router, I should be able to ping 172.18.1.2. That's on the top router. Success. I should be able to ping 172.17.1.1. Success. So I know that both legs of my triangle here are good. I already tested my third leg of the triangle, but I moved around some cables while I was debugging, so I want to retest. So I'm going to go to the top router now. And now I am on the top router, and I should be able to ping 172.16.1.2. Success. Okay, our link layer is up, our IP addresses are configured. Now we just need to configure our routing, because from the top router, if I ping the 172.17.2.1 IP address, which is the loopback of the middle router, it will fail. And the reason is because I do not have a route to get there. So let's configure our static routing. Conf T IP route 172.17.2.1 255.255.255.255. This is our destination subnet. 172.17.2.1/32. Now the question is, what is our next hop? Let's go back to our diagram. And from our top router, our next hop for 172.17.2.1/32 would be 172.16.1.2. Now let's figure out our next static route for the other loopback. From the top router, in order to get to 172.18.2.1/32, our next hop should be here, 172.18.1.1. IP route 172.18.2.1, 255.255.255.255, 170. Next hop is 172.18.1.1. Now here's something interesting. We just configured the top router so it knows to get to the loopback in the middle router to go here, and to get to the loopback on this router to get here. But these routers, the middle and bottom routers, they need to know how to get back. In this case, they already know how to get back because when you're originating a ping, you use the IP address that is physically closest to the destination. So because the top router knows to get to the middle router's loopback, it should send the ping out at serial 0 interface. It will use as a source IP address 172.16.1.1. So let's see if our ping succeeds. Ping 172.17.2.1, and it succeeds. Let's do a debug IP packet. Ping 172.17.2.1. What did we just do? We typed in debug IP packet. That is the debug commands in iOS are commands to give diagnostic output. It's used by the developers. As a network engineer, you can use it too, but you have to be extremely cautious in production. In this case, what debug IP packet does is every time you send a packet, it will tell you the information in the packet. Now, on a router like this, where we just sent 10 packets through it, that's okay. But people run routers that run tens of thousands or hundreds of thousands of packets per second through it. If you do a debug IP packet on those routers, the router will go to 100% CPU and you will suffer a network outage. In fact, the network outage will be so bad you won't be able to type in no debug all, which is how you stop debugging everything. So I'm showing the debugs, but only do the debugs in the lab until you really understand which debugs are dangerous and which debugs are not dangerous. And debug IP packet is one of those very dangerous debugs that you don't want to do. Okay, so let's go ahead and look at our debug output. Here's a packet. The source is 172.16.1.1, which is local. Let's go ahead and look at our map. 172.16.1.1 was the serial interface closest to the middle router. So as we expected, it used the source IP address of the interface closest to the middle router. And our destination is 172.17.2.1. The length is 100, and it's sending the packet. The next packet we get back is a response. 172.17.2.1 is the source, which is this loopback interface on the middle router, and the destination is 172.16.1.1. So this is one ping, our request and our response. And we repeat that 5 times. Let's debug IP packet detail. Ping 172.17.2.1. Now we print out more information about the packets. Our source IP, again, it's 172.16.1.1. Our destination 172.17.2.1. We're sending it out our serial 0 interface. It is an ICMP packet, Inter-Network Control Message Protocol. That's what ping uses. It's a diagnostic protocol. Type 8, which is probably echo request, code 0. And then we get a response from 172.17.2.1, which is that loopback address, back to us. And it is ICMP type 0, code 0. Probably an ICMP echo reply. Okay, so that's debug IP packet. Now our debugs are turned on. No debug all. We'll turn off all debugging. Great. So we can ping this guy. Now let's go back and look at our map. We want to make sure we can ping this loopback interface over here. Ping 172.18.2.1. I'm sorry. I want to, ping 172.18.2.1. Success. Now let's see if we can ping this IP address here, 172.17.1.1. Ping 172.17.1.1. Nope, we can't ping it. Why not? Let's do a show IP route. So the target that we are looking for is 172.17.1.1. 172.17.2.1 we have a route for, the /32. But that's the only thing that we have a route to inside the whole 172.17.0.0 class B. Because that's a class B IP address. You know, we never actually created a static route to that guy. So let's go ahead and create a static route, conf t IP route 172.17.1.1, 285.285. I'm sorry, the network is 1.0, 285.285.285.0, and our next hop is 172.16.1.2. But looking back at our map, we actually have two routes to get to this location. We can get there through this one, or we can get there through this one, and they're equal cost. So for maximum efficiently, let's configure the other static route as well. IP route 172.17.1.0, 285.285.285.0, 172.16.1. I'm sorry, 172.18.1.1. Ping 172.17.1.1. That's interesting. I'm getting 50% packet loss. Every other packet is being dropped. Ping 172.17.1.2. Why am I getting 50% packet loss? Let's go ahead and do our debug IP packet. Ping 172.17.1.1. So here we sent our first ping. Our source was 172.18.1.2, and our destination was 172.17.1.1. We are sending it out the serial 0 interface. That ping failed. There was no response. You see that? So when we're pinging from this IP address to here, it fails. But then the next ping, we ping from this IP address, 172.16.1.1, and we get, and our destination is the same, and we get a response. Here's our response from 172.17.1.1. So when we're pinging from here to here, it succeeds. Now, when we're pinging from here to here, our packet starts at this box, and it gets to this box. This box knows that this is one of its local interfaces, so it responds, and it responds back to this IP address. The middle router has a route to this IP address because it's on this directly connected subnet. But let's take a look at the middle router. Now logged into the middle router, show IP route. The only routes I have are my directly connected subnets. Serial 0, Serial 0, Serial 1, and the loopback. So when the ping came from 172.16.1.1, this router knew how to respond because here's the route for 172.16.1.0, the whole /30, which includes the IP address 172.16.1.1. But when the ping came from 172.18.1.2, my router does not have any routes for 172.18.1.2 because I haven't configured any static routes on this router. So let's go ahead and configure a static route for the 172.18.1.2/29 subnet. We'll configure it back towards this router. We'll just configure one route. IP route 172.18.1.0 255.255.255.248. It's a /29. Next hop is 172.17.1.2. Now let's see if we can ping 172.18.1.2. We can ping it. Great. Let's go back to the top router. I moved my console. Let's ping 172.17.1.1. And now all my pings succeed. Oh, there's all my debug. No debug all to turn it off. Ping 172.17.1.1. Success. So my routes to my destination were actually correct. But in order for pings to work in the network, and in fact, in order for most communication in the network to work, the traffic has to go in both directions. You have to be able to get to the target, and the target has to be able to get back to you in order to see the response. There are occasionally a few applications that actually send the traffic in one direction, but 99% of the time, when you're talking to something else, it needs to talk back, if only to acknowledge it. Even if you're going to a web server, the web server is sending you the data. You're not sending any real data to the web server, but you're actually sending your request to the web server. You're telling the web server which URL you want to download, and then the web server is sending you the data. So most communication on the internet, the information goes both ways. So the routing needs to go both ways. So this was static routing. And you can see how error prone this is. This is about the simplest network you will ever see. And we had to configure 1, 2, 3 static routes on this router. If we configured all of our static routes, we would have configured 9 static routes on our 3 routers. And our 3 routers only have 3 links plus 3 loopbacks. That's a lot of configuration. Static routing is not it's a very error-prone way to build a network. You can build the network with complete efficiency, but it's incredibly error-prone. So let's go ahead and look at one other thing. Let's do a show version. This is 12.2.8T5, the iOS version. Let's do a show IP Ceph. Ceph is not running. What is Ceph? Ceph is Cisco Express Forwarding. The route table is optimized for being updated by routing protocols. So our static routes can update the route table. If we had a dynamic routing protocol, which we'll talk about in a lesson or two, then it would update the route table. But the route table is not very efficient for actually forwarding packets. Because if you need to forward a packet to 172.16.2.1, you look at the routing table at this line, and 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 at this line. Oh, that's a match. Let's go ahead and forward it out the loopback 0 interface. That's not very efficient. Ceph is Cisco Express Forwarding. If you enable Ceph on your router, then it will create a special forwarding table, which will forward the traffic more efficiently. Conft IP Ceph. Now what this did is it has a different routing table. Show IP Ceph. here is what the Ceph table looks like. It has a default route drop because there is no default route configured on this router. And it has 172.16.1.0/30 is attached out serial 0. 172.16.1.0/32 is it receives it because that's its own interface. 172.17.1.0/24 has 2 next hops that you can send to out 2 separate interfaces. 172.18.1.0/29 is an attached or connected subnet. 172.18.1.0/32 is receive. This is a more efficient routing table, or this is a copy of the routing table, but it's copied in a way that is efficient for the router to forward. So by enabling IPsef, you actually increase the performance of your router by a factor of 10. High-end routers have IPsef enabled by default. For example, on a 7200 router, Ceph will be enabled by default. But as you can see here on this 2511, Ceph was disabled by default. So if our CPU was running high, and show proc CPU. So in our case, this router is just working in the lab, so our 5-second CPU average is 0, our 1-minute CPU average is 2%, our 5-minute CPU average is 2%. So we have plenty, this is show proc CPU. So we have plenty of CPU capacity available. But, you know, if this is a lab, we don't have any traffic going through this box. This box could very easily be melting down. So by enabling IPsef, we can increase the performance by a factor of 10. That's all I have for today. Thank you.